Part of Kindness Week, adopt a local restaurant. Local today. If you like, if you want to, write a good review or do something to give them some love. This is my vintage T-shirt for the day. Woodstock '99. Doesn't seem so vintage to me, but 22 years ago it's kind of vintage. So, and Mrs. Rosengren was actually there. She got this shirt at that concert, so at that festival. Pretty awesome. How did yesterday go? Let's practice it. Let's kind of recap what we know and really just like focus on just that idea and make sure we can handle the mechanics of dealing with the difference quotient and the limit that goes along with it. Okay. So I think the way that this would work pretty well is to just kind of start here where we left off on page 116. Now I know that you guys in front of me might have like jotted a lot of this stuff down separately somewhere. If you want it all in one place, maybe take tonight or something. Like I won't have you do anything outside of class for sure. Take tonight or take tomorrow at home when you get a chance, and maybe transfer some of that stuff over. Even just like rewriting it again, I think might be worthwhile. I don't know. That's kind of up to you how you want all of your notes to work. But kind of, the big idea that I want us to see is that we've got a way where we can like, I say it a lot, but like actually like pause time and see what's happening in something that's actually moving. Right? We can watch things change. Right? Calc is a study of change. I can watch something move. Right? I'm going to watch, like, let's say something moves in this pattern. Right? I can freeze time and say, hey, what's happening right now? And it could be at any of those points. It could be at the top. It could be on its way up or on its way down. And then think about motion is a good way to kind of visualize whatever's happening. And we'll look at all kinds of functions. It doesn't have to move like, you throw a ball up in the air and it falls back down, kind of upside down parabola, but it's a good place to start. So, but the idea of like how I got us to that point, was that okay? Where I kind of drew that graph and I said, okay, here's a point here. Here's what they struggled with, like trying to figure out the slope of this line that only hits it once. Okay, well, let's take a point somewhere else on the function, find that slope, because now I know 2 points, and then just start moving it closer and closer and closer and closer. Because as this point slides down closer and closer to this one, the slope of that secant line starts approaching the slope of the tangent line. And if we could make those points the same, right? If I have some kind of picture, right? I've got a picture, don't draw this, but right, if I wanted to know like the slope of the tangent line right there, this is what we did yesterday. We said, all right, well, what if I just pick a point over here, find the slope of that secant line, which is not the same, obviously. The green one's a little steeper than the red one. But then we said, well, what if I just move this point a little closer, and 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 a little closer. As I start drawing lines through those points, you can see that the black lines start to approach the red. And that's kind of the idea. And as nice as it is to be close, we want to be perfect. And the only way to do that is for us to make those points one and the same. Now, the problem is I can't do this in 2 dimensions, right? Like, there's no depth on this whiteboard, right? There's no depth on that piece of paper. And so what's really happening is that they're like becoming one. They're doing that. And of course, we can't find the slope between one point, but we can let the limits take care of all of those mechanics for us. Like we're gonna get so close, God, they're gonna be so super close that they feel like they're the same. And it's good enough for us. Is that cool? Are we okay with that? Like the idea is to say, okay, I've got this point right here at some x. I've got this point right here, some horizontal distance away. So call this x plus h. And all we're going to do is we're going to make this smaller and smaller and smaller and smaller. The distance between those points is going to get smaller. And as those points get closer and closer together, the secant line is going to almost become the tangent line. And once they are on top of each other, then the tangent line and the secant line are the same. Which is why our limits, the difference in the y values, the difference in the x values, just the slope, we're going to let h go to 0. We can't actually let it become 0 right away, right? Because we'd be dividing by 0 if we did that. But we know the limits don't really worry so much about what actually happens at 0. But we're going to get so darn close, it's not going to make a difference. Okay? And what I want you to, you have to believe that first. And if there is anything about what I'm saying that doesn't make sense, you have to speak up now, because otherwise I think you believe it. You're totally on board with the fact that those two lines are going to be the same, and that the slope of a tangent line, wherever it is, right there at -4, the slope of that line is the derivative at that spot. The slope of the tangent line and the derivative, I'm saying the same thing. Those two mean exactly the same thing. The derivative is just the name for the slope of the tangent line at any point on any continuous function. Because that's the basis of calculus. And if we don't understand it, one, but believe it more importantly, two, then I have to stop and I have to fix that. Question. Thank you. Only one spot, exactly. Because what we tried to do, I'll jump on the whiteboard just for a second. I wonder if it has the stuff from yesterday now. So like we had this problem that Newton and Leibniz were running into, and they said, okay, like what if I pick a point right here and I want to figure out what that line is, right? That only hits it once. And a lot of it kind of boils down to the fact that if this is something moving through space, and like seeing movement is an easy way to picture this, that if I kind of pause right there, if I just click and stop right there, that's the direction that that particle's moving at that moment in time. And of course, it's going to change its direction as it moves. I mean, but think about a straight line, right? That's the direction that something is moving in. That if we could figure out what the slope is of this line, I know how fast it's moving in how fast it's changing its direction. When we think about rates of change, right? Change in y over change in x, right? Slope. And the issue that they ran into when they were kind of contemplating these ideas back before calculus was even a thing, is that they knew slope formulas. They knew a lot about lines and functions in general, but they said, well, if I'm going to find the slope of this line, I need that point right there. But I don't know that point. I know nothing about that line other than the fact that this point x, f of x, exists. If I only know one point, I can't find the slope of a line, because take a point. How many lines can you draw through it? As many as you want, right? An infinite number of points, infinite number of lines. But if I had a second point, I could find the slope. And they said, well, okay, well, I don't know anything about the blue line, but I do know everything about that black curve, whatever that is. I could find a second point over here, like close to that, right? I could go like just a little above it. To say, okay, I've got a point right there and right there. Let's talk about the slope of this line, if that was straight. And the blue line and the green line are kind of close to being the same. Are they the same though? No. But if I could measure this distance, that horizontal distance right there, so I call this x plus h. So this is f of x plus h. If I could find the slope between these two red points, let's say, the slope of the green line and the slope of the blue line will be pretty close. But they're just not exactly the same. But if I started to inch this, like let's say this point is fixed because that's the slope that I want. If I start moving this point closer and closer, what happens is we start getting lines that start getting closer and closer to being the blue line. Right? Those black lines start getting closer and closer to becoming the blue line. And what happens is that as this distance gets smaller, what's happening is that h is going towards 0. Now, of course, I can't actually let h become 0 because then I'm finding the slope at one point. And that was the initial problem that we couldn't handle. I can't say, oh, let's find the slope between 2 points if I don't have a second point. And so what Newton and Leibniz started to think about was, okay, well, all right, I have 2 points. I've got this point, but then I'm going to take this one, and I'm going to take this one, and then I'm going to take this one, and 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 this one. And I'm going to see what's happening as we approach that spot. As I get closer and closer, as this point gets closer and closer to this one, what should happen is the green line should start to kind of flatten out a little bit and become the blue line. Now, I can't actually let them become the same points. I'm just going to let them approach the same points by taking the limit. And that's all we did. We took the difference in the y values, the difference in the x values. So x plus h minus x, the x's just canceled out, which is why we ended up with just h on top. Okay. And what we saw is that it was the limit of the difference quotient. It was just a name for it, but it's just the slope. Right? The slope of the tangent. And what we tried to do with this one right here is just see what happens if we actually try to evaluate that limit by hand. Like, what if we just evaluate the function? Evaluate that whole fraction by plugging in x plus h, by plugging in f of x, by dividing by h, trying to expand, simplify, and see where it goes. And that's kind of this process that I want to work through today on page 117 here in a second, but I want to finish up 116 first. Because what we figured out is that if this is the derivative of that function that we were working on, right? So you could call this f, the derivative of f of x. You could say that out loud. What was the other name? Do you remember what we called that yesterday? With that little like apostrophe looking thing? F prime, good. So I'm going to say that a lot. I'm going to say f prime of x. It's just a little faster than saying the derivative of f of x, but they're one and the same. What we figured out is f prime of x, the derivative of f of x, is just the limit of the slope. And so on, what is this, 115 maybe, something like that? Maybe 116. We figured out that, and when I say we, I mean, Newton and Leibniz, separately across a continent, so cool. They kind of came up with the same idea that, hey, I can't actually divide by 0. I can't make them the same point. Man, if I could get so close, it wouldn't make a difference. That the green line, as it approaches the blue line, they become one and the same when I get there. Because what this represents graphically is the slope of the tangent line. And this is kind of how we ended class yesterday. But this is the definition of the derivative. But when I see the word derivative, I think slope of the tangent line. Those two in my mind, I'm saying the same thing. Does that make more sense? Does that clear up some things? Okay. So here's a function. We can find the derivative, yeah. Any point. It becomes its own function of x, whose sole purpose is to only give me that. The slope of the tangent line at whatever x value you so choose. So they're going to give us an f of x, or g of x, or h of x, whatever. We're going to find the derivative by kind of going through this process, evaluate, expand, simplify. Don't worry, we'll find shortcuts really soon, like next week, and be able to use those right away. Chapter 2 is really short. It's just kind of an introduction to the derivative. But you're right, like, give me a whole function. I can find a whole derivative, another function of x, that plug in any x you want. It'll have us stop at the function at that exact point, and it'll give us the slope of the tangent line. Whether it's positive or negative or 0. Of course, I need an x value for there to be a slope there. So I want the function to be defined. And hey, continuity just makes that even better, right? Because we're talking limits, I need continuity. So a lot of the things that we look at really here on out, we'll be looking at continuous functions everywhere, or at least continuous sections, parts of the function that are continuous. So we don't have to worry about holes and asymptotes and weird stuff going on. Good. Other clarifying questions? Hopefully that helps. All right, let's actually try some of the mechanics of this. But I want to finish up this part down here because I hope that this is going to help. But the thing that I want to make sure we have on page 116 is the work that we did at the top of page 116 to say, okay, look, we're at -4. Like, here's a function. We figured out the derivative. What was the value of the derivative at that spot? What's the value of the derivative at this spot? What's the value of the derivative at this spot? And this is where, I don't know if you did this yesterday when you were at home, but we said, okay, let's go to -4. Like, okay, I got this whole function, but like stop right there and imagine what it would be like to try to draw the line that only hits the graph in that one spot. And try to get a sense for what the slope of that blue line might be. Well, what do you think? Is that slope going to be positive or negative? Let's start with that. Positive, going up. Perfect, right? The line's going up. Okay, so I should get a positive number over here. Let's see what kind of positive number we get, and all we have to do is plug it in. And we did this in class yesterday, so if you were in class yesterday, this is kind of recapping something. Okay, that's blue because I drew blue lines. That's 4. F prime of -4 is 4. Now, that doesn't give me anything about the y value. It says, okay, here's the x value. Give me the slope of the tangent line at that spot. It's kind of like skipping over, hey, f of x, right? F of -4 is the y value. I don't need that necessarily if I just want the slope. The derivative does that. Right, same thing at -2, right? Stop right there and think about what it would take to draw a line through that point that only hits that function once. Right? Secant lines hit them twice. Tangent lines hit them once. And that was the issue that they ran into when they were kind of first running through these ideas of, okay, like how do we stop time to figure out what's happening? Well, I only have one point then if I've stopped time. I don't have space. I don't have the gap between. What is the slope of that line, do you think, that's green there? 0, right? That's a perfectly horizontal line. And what's cool is that the derivative is going to back up that idea. Right? -2 times -2 is 4. 4 minus 4 is 0. Right, go to -1, put a point, draw what you think would be a decent tangent line, and think about what kind of results we might get. Now, what do you think, positive or negative? For the red line's slope. Yeah, it's going down, right? Going down from left to right. So I should get a negative answer here, and we do. All right, we get -2. If I know the slope of the tangent line, I know what direction the function is moving at that time, right? If the slope is positive, we're going up. If the slope is negative, we're going down. Look at the function, right? Slope is 0, maybe we're at a relative extrema somewhere. Okay. And now we have those 3 numbers. Now we can use them at the bottom of page 116 to actually find the equation of the tangent line, which was kind of our first initial issue. That student was sitting there and said, how am I going to figure out what this line is if I only know one point? Well, if I want to know an entire equation of a line, I know the x value. So that's good. What's a good way, let's say, to write the equation of any line as simply as possible? I should even say as easily as possible, with as little work as possible. What's a good setup? There's one. Absolutely. You want to write the equation of a line, we can write it like this. And if you do that, there's a couple of things that we need. I need a slope, and I need a y-intercept. I gotta know where this thing is going to run into the x-axis. Okay, well, the slope of this line, what's that going to be? Or the derivative at that spot. This is always going to be f prime of whatever that x value is. Plug it in, and I'm good to go. But do we know the y-intercepts of that kind of like, we just sketched out that blue line, that first one? We could estimate it, but we don't want to estimate. We don't want to be wrong. We probably have to solve for it, right? We'd have to plug in the x. Cool, I know that, the -4. We'd have to plug in the y, which means we'd have to like go back to the function or go back to the graph and look for it, and then do a bunch of algebra to find the y-intercepts. And that'd be fine. It would work, absolutely. But I think there might be an even easier way for us to write the equation of a line that doesn't require all of that algebra at the end. What's the other way to write the equation of a line that isn't slope intercept? Point slope. And I think you're going to find that this one just a bit faster. Because m is still going to be that derivative, right? That's a big part of what we need. That's just going to be the derivative at whatever that x value is. And all I need is a point, right? Some xy. Now, if you don't like that you're not set equal to y in that case, then you can use an alternative version that's y equals, you just add the y1 to the other side, mx minus x1 plus y1. If that makes you feel better, that's cool with me. Either one's fine. I think people gravitate towards this one because it's y minus and it's x minus. You don't have to worry about remembering time. But either way, we still need the y value, okay? But what we do know, and so I'm going to write a couple things down, all right? I know that the x value at that spot is -4. And I know that the slope, which is the value of the derivative at that spot, we figure that out that was 4. And if I can just figure out what the y value is, I should be able to write the equation of the line and then be done. I don't have to worry about the algebra that happens in the background. So what's that y value? They gave you a picture, right? Sweet. Okay, cool. Use it. They wrote the function too, right? They said f of x is negative x squared minus 4x, whatever it is. So you can always plug it in if you want. But if I know the point and the slope, because I know the derivative, then I can just write the equation of the line. Now I'm going to go back to this one. If you want to use this one, go for it. You want to slide the y value over, but this is pretty common that we would write it y minus 1, right? Y minus y1 equals m x minus -4, so x plus 1. Again, add that 1 to the other side if it drives you crazy. Distribute and simplify if it drives you crazy. But calculus is about working as efficiently, right? Working smarter, not harder. Absolutely. And so when they ask us for the slope of the tangent line, boom, derivative, and I'm done. But if you want me to have the whole line, man, I need a point, and I need the slope. So let's go to -2. What's the y value at that spot? 5. Cool. So nice when they draw a graph for us, we don't even have to plug it in. But if they just gave us a function, we would just plug it in, see what happens. What's the slope of the tangent line at -2? 0, because the value of the derivative at -2 is 0. And if I know both of those things, I can come up with the equation of the tangent line that looks like that. Now, the first one on the left there, right, that's a perfectly fine way to write that down. I love it, looks great. I know the slope, I know the point, I don't have to do any work. But like I said, if you want to distribute and simplify and move stuff around, go for it. The one there in blue in the middle, what's going to happen to that whole right side? It's all going to be 0. So if you want, I think if you do have an easy way to simplify that, just call it y equals 5, right? Because add the 5 over and everything else is 0. The horizontal line, so y equals whatever. But seriously, the blue line before the one I just boxed in is fine. It really is. It actually tells me more than y equals 5. Because when I write y equals 5, I don't know where the function is at that spot. I don't know what the x value is. I know what the y value is. It's going to be 5. But I don't know where I am on this function necessarily. And so some people, and I totally get why, actually prefer the one before it, even though it's nowhere close to being simple. Try the last one yourself. Let's see if you can do it. I got to peek. I think I know what it is. So I just wanted to have that quick conversation. Now we can get back to actually working through the derivative by hand with the limit and kind of going through this process. And to do that, I'm good with just jumping right to the next page. I think jumping right to 117 looks good. We'll see how far we can get working through both of these in the handful of, a couple of dozen minutes we have left. But how are we feeling? Is that okay so far? Okay, good. All right, scroll a little bit, and my goodness, if a calculus teacher is going to shout at me, this is how I would shout. My good, like, look at all those capital letters, man. Caps lock is just right next to the A. You can press that next time, right? But seriously, like, you hear derivative, slope of the tangent line. Slope of the tangent line, derivative. They are one and the same. Now let's actually try it out. Let's try the one on the left first. And so what I want to make sure that we do when we're working through this process is right away let whoever's reading this know what you're finding. By starting my work with that f prime of x, by saying, hey, look, here's what I'm going to do. I'm going to find the derivative. Now the rest of the work, I know what you're trying to do. And here's what it's going to look like. I think, early on especially, I think it's a very good idea to write down just the setup in general with the difference. F of x plus h minus f of x all over h. Now I'm going to use as much space as I possibly can by going this way. Okay. Now stop and pause for a second. Look at your function. 2/3 x plus 3. What kind of function is that? Okay, cool. So I've got a line graph. I'm going to draw a line through a point on that function. What's the slope going to be? 2/3. That's the slope of that line. We better get 2/3. When I do this process, the end here should just be 2/3. It's linear. The slope of any line on that line is just going to be whatever that line is. So let's see how that plays out. So the limit as h approaches 0 of, okay, cool. Now, first thing we're going to do is we're going to evaluate. We are going to actually change every x to x plus h and see what happens. Okay, so what's boxed in red is what's happening right here in red. 2/3 parentheses x plus h plus 2. That's f of x plus h. Any x that's in that function gets replaced with x plus h. Now, don't forget, we still have to subtract whatever f of x was. And parentheses are necessary with any polynomial because we got to make sure that we subtract the 2/3 x and the plus 3. All right, so what's boxed in green there is what's written in green, and then just all of it. And we're going to bring this limit along with us for a long, long time until we actually get to the point where we're okay to plug it in. And that's always the goal with the limit, is eventually, like, let's divide away the problem. And of course, the problem is being the h on the bottom going to 0. So let's figure out a way to isolate that h up top so we can divide it. And so step 1 done, evaluate. Step 2, expand. Get rid of all those parentheses so we can find ways to put some stuff together. So the 2/3 gets multiplied into the x and the h, so 2/3 x plus 2/3 h. I like to keep my variables out of my fractions that are only constants if I can. But if I was going to put it within that fraction, it has to go up top. Right? I'm not dividing by x or dividing by h. I'm multiplying it through, so that would end up on top, if you did it. Bring the plus 3 down, right? We got that plus 3. All right, so the 2/3 went in. Now the negative goes in as well. Minus 2/3 x minus 3 all over h. Yay, done. Evaluate, expand. The only purpose in expanding is so we could combine some like that. Let's simplify anything that you see that goes together. what do you notice? Do you see any like terms that we can connect? Nice. We got a 2/3 x and a negative 2/3 x. Cool. What else? Positive 3 and negative 3. And all of those are all opposites, so they're all going to add to 0. And so what's left over is just that 2/3 h up top and an h on the bottom. Now, because we knew what our slope was going to be no matter what, it wasn't really a function of x, it was just going to be some constant. That's why we don't have any x's left over, right? Because it doesn't matter where I am on that line, the slope of that line is 2/3. But we still have to get to a point where we're okay dividing away the h so we can plug it in if we need to. And we're good. It's already kind of factored just because there's only one term there. So we are in a very easy situation when we have a linear graph because the slope is constant. Take any other graph, and the slope is not constant, which means it's going to be a function of x. But really what's happening here is we get to this. The limit of a constant. Is there a place to plug in 0? Awesome. Then the limit of a constant has and always will be just that constant. There it is. There's that 2/3 that we were expecting. Okay, so it doesn't get much simpler than slopes of lines. Because we already know what those are ahead of time, so we know what kind of answers we're going to get. But if you look at the one on the right, don't draw this, but I just want you to kind of visualize it, right? I'm making it kind of wide because it's 1/2 x squared. There's that graph somewhere, right? It's kind of floating around on the plane somewhere. But imagine kind of moving along that graph from left to right. Imagine you were a point kind of walking through that space. You're going to go down, and then you're going to level out, and then you're going to come back up, right? Your slope, how your position changes is going to be different every step you take. It'll be a little steeper, and then a little flatter, and then completely flat, and then back up you go. So when we find the limit of this difference quotient, we find the derivative. Because the function is changing, the derivative is going to change it. And that's kind of my hope, my plan, is that I can use the derivative to figure out exactly how it's going to change. By starting with the very first thing, the derivative. Starting with f prime of x sets the tone for what you're going to find. Now, I'm going to write out the whole thing again just so we can see it. But you'll probably get to the point where you only do it once, and then you say, oh, you want me to find 5 derivatives? All right, I'll write it the first time, but these last 4, I'm just gonna jump in. Now, this might be a little bit trickier for me to try to squeeze it all in, so I might end up erasing some of that stuff on the left, but I'll give you a chance to see it for a second. But the idea is to first do that, right? Drop in x plus h anywhere you see an x. 1/2 parentheses x plus h squared minus 2 times x plus h plus h. There's no x attached to that 3, so that's why we don't have a little plus h there. And the thing that I see the most early on, calculus students that get this stuff wrong, is they just add a plus h, like at the end, rather than changing x to x plus h. Right? You're evaluating the function, so just be careful there. So there you go. What's in blue is what's boxed in blue. Now, what's in purple is me subtracting all of f of x. 1/2 x squared minus 2x plus all of it. No, yeah, send it out. Are we cool with that setup? Does that make sense? You all right? Now you expand. This is where things take a hard turn for those of us that don't love binomial expansion with Pascal structure. But I cannot stress enough how important this is to helping you work through that x plus h squared, or an x plus h cubed, an x plus h to the fourth, a whole lot faster. Okay. Second number in is the line you want to be on. Those are my coefficients. And the exponents go from 2, 0 to 1, 1 to 0, 2. And hopefully you get to the point where that happens so fast. But if you need to do x plus h times x plus h and actually multiply it out, I'm totally fine with that. But I would do it like over here, right? Find some separate space outside of your derivative so that you can simplify what that looks like. And in case you need it, right? X plus h squared is x squared plus 2xh plus h. And maybe it might be to your benefit eventually. Maybe we'll do this if we ever have like a few moments of downtime. It's like create a space somewhere where we have some expansions all worked out. Squareds, cubes, maybe quartics. You usually don't have to do more than that. Powers of 4 is about as high as up because we're going to go by hand. Okay, but I want 1/2 of that. So I'm going to do that right now. I'm going to take 1/2 of all this. So I'm going to take 1/2 x squared plus 1/2 of 2xh, so just xh, plus 1/2 h squared. Here comes the expansion, right? That's what we're doing now. So I'm taking this side work down here, and I'm just cutting it in half because that was that leading edge. And I just like to try to expand everything all at once. This way I have one step for everything. So I'm going to multiply in the -2, the -2 times x, and -2 times h. Plus 3 is just plus 3. And then minus all of f of x. So minus 1/2 x squared plus 2x minus 3. Oh. Evaluate, sweet, done. Expand, that's the hardest part, I think. But if you do the expansion right, a lot of stuff should simplify, and you'll see what happens. We had this conversation yesterday, and we'll have it again, but let's take a look. Do you see anything up top there that we can put together? The 3's, yeah, absolutely. Plus 3 minus 3, good. Those are gone. What else? 2x's, good. We have a positive 2x, and we have a negative 2x, so those are gone. Beautiful. 1/2 x squared and negative 1/2 x. And all of them add to 0. And that's always going to be the case if we're doing this right. And if you notice about what's circled there, everything that I circled, all of those like terms that you said canceled out to 0, all of them have 0 h's. There's not a single h as a factor in any of those. And that is always going to be the case. But if that's true, if everything that we just got rid of doesn't have an h, then does that mean that what we have left, that everything does? Well, those aren't necessarily mutually exclusive, but let's see what we get. xh, I just like to take a second and write it down, see what we're working with. Plus 1/2 h squared minus 2h all over h. Yes, they do. Absolutely they do. And what's great is that that is always going to be true as well. Everything you cancel out will have an h. Everything that's left will. Because the problem that I have is plugging in 0. Can't do it. So if I could divide away h, right, h on top, h on bottom, then I don't worry about it because I've removed the issue. Okay, well, how do I divide away h? I'm going to factor it out. So that's what we're going to do. We're going to pull that h out from the top and see what's left. And as clunky and cumbersome as this process is, what's nice about it, when we're dealing with polynomials, it's always the same. You kind of get into the mechanics of it and it works really well. So what do we have left? We have an x, we have a 1/2 h, and we have a -2. That must be hard to see. X plus 1/2 h. Because now the h's are gone. And once the h's are gone, then the only thing that I have left is what's inside those parentheses, the x, the 1/2 h, and the -2. Something bright. And we got rid of the problem. So is there any issue now in actually plugging in 0? Oh, this might be too bright. Sweet. So let's do it. X plus 1/2 times 0 -2. Get rid of this just because I'm out of space. Minus x minus 2. That. And that's your derivative. And that's your function of x, right? That says that anywhere on this function, stop, pause, draw the line that only hits it once. What's the slope of that line? Whatever x value stopped at, minus, which is crazy that it works out that way. And your minds are going to be blown in like a week when we actually start looking at, all right, how do I get from f of x to the derivative? Like that. We're going to start finding some patterns. And we're going to be able to jump from the function to the derivative in one step. Okay? All right, we have a few minutes. I want you to try one. I'm going to skip that question down there at the bottom because I want to give you a chance to try it. Jump to page 121. Because I just want to stick with polynomials. You'll see like 118 has a square root and a rational, and those are just a little trickier. But page 121, number 1, I'll leave this up just for a second. Try that. Okay. Try that left-hand column. Don't worry about the one on the right. Okay? So you've got this function x cubed plus 2x. Find the derivative using the limit definition of derivatives. When you're done with that, here. Oh, but do the bottom part to the equation of tangent line. If you get there quick enough and have. Of course, folks at home, if you've got questions, let me know. So I'm going to erase this and I'm going to do the work. We'll come back to those square roots of rational. In case you need it. One, three. Now, I definitely took my time through the algebra there. You might feel okay going a little faster. Potentially skipping from like this blue line after the expansion to this blue line and back. Like saying, all right, you know what? I see it. I got my x cubes are gone. I got my 2x's. Those are gone. And everything else is left. So, hey, let me factor out the h right now. See what I have left. That's fine. And then, hey, you know what? If I divide away those h's, I know what's left behind. Let me skip from this blue line to this one. And just plug in h. Plug in 0. I'm cool with that too. So whatever you're comfortable with, I have to see a few things for sure. I need to see the evaluation, where there's the x plus h goes in. I have to see the expansion, and I have to watch h go to 0. Other than that, I got, see the h come out, and then watch it go to 0. So find what's comfortable for you. I don't think there's any more you would ever need to show than that, but you could show a little less if you're like, oh, all right, I kind of get this. I'm getting the hang of it. And that's what we're going to do. We're going to take some time. We're going to get the hang of it. I'll show you what to do with square roots. What are we going to do? We're going to rationalize it, and h is going to pop out. It's going to be great. What are we going to do with rational ones? We're going to find a common denominator, and h is going to pop out. It's going to be great. But polynomials are really easy. Easy. All that easy. And that's it. Cool. So nothing you have to do. I will see you tomorrow. Thanks, everybody. You're welcome. Have a great day. Thank you. Yeah. I had no idea. Later, boys.
Thank you.
You are welcome.